So in this video, we want to look at volumes of revolution using what's called the disk method. And for video one, we're just going to develop the concept or the formulas that we need. And then in subsequent videos, we'll show examples of the application of the method. So here's the idea. We want to find the volumes of revolution. And a volume of revolution is simply this. If we're working in the XY plane, for example, and we're going to work over some interval from A to B, and we have a curve in the XY plane, the idea is that we want to revolve that curve, usually around either the X or the Y axis, although we can choose to revolve around other axes. But in this case, for example, we're revolving this curve around the X axis. And if we do that, what we wind up with is a solid swept out by revolving that curve. We revolve the curve around the axis, and it generates what we call a solid of revolution. And what we want to do is find the volume of that solid using tools from calculus. So here's another example. Here's a curve. In this case, it's the square root of x, but the actual curve doesn't matter. It could just be any curve f of x. You revolve that curve around the x-axis, and you wind up with a cone that's shown here. So the idea is, given a curve in the xy plane, revolved around either the x or the y-axis, how do we find the volume of the solid constructed by revolving that curve around the axis? And the idea is what we're going to do is take the region under the curve, and we're going to break it into n rectangles. So we're going to do n rectangles. And if we draw in just one of the n rectangles, so the idea would be take the entire region under the curve, break it up into n rectangles. You choose what the size of n is. You choose how many rectangles to break it into. We usually just draw a picture of one of the n rectangles, and we call that the representative rectangle for the region. And then what you do is revolve the n rectangles around the axis, and you calculate the volumes of each of those revolved rectangles. And what we want to notice is when we revolve a rectangle around an axis, we actually get a cylinder or a disk. And the idea is we know the volume of a cylinder. The volume of a cylinder is pi r squared, the area of the circular face of the cylinder. So if we have a cylinder, you do pi r squared. Here's r. Pi r squared gives you the volume, the area of that circle, and then you multiply by the height of the cylinder. So it's pi r squared h. So we know how to calculate the volume of a cylinder or a disk. So we just can calculate the area of each cylinder or each disk, add them all up, and we have a approximation of the volume. And then we want to look at tools from calculus to get the exact volume. So that's the idea. So on the next slide, let's just kind of develop the formula. So we'll take the picture that was on the bottom of the previous slide, and we say, hey, I want to find the area under this curve. Let's suppose I don't know what the curve is, so we'll just say it's f of x. And we are going to run it over some interval from A to B, so we don't care about the exact numbers. I want to revolve the curve f of x around the x-axis over some closed interval from A to B. To approximate the area, I'm going to break this region up into n rectangles. We're going to revolve the n rectangles around the x-axis, add up the volumes of the resulting disk to approximate the area. So here's the representative rectangle. We just do one rectangle to represent the n rectangles that we'll be breaking the region into. And what I want to recognize is when I revolve this rectangle around the x-axis, I'm going to get a disk. And here it is shown in green right here. I get a disk. And that disk is going to have a radius. And what I want to recognize is that the radius of that disk is going to be y, the y coordinate of the center of the disk. So if this is x sub I comma y sub I, right at the center of this representative rectangle, then the height of this rectangle is y sub I, but that's going to be the height, or the radius, sorry, it's going to be the radius of the disk I get when I revolve this rectangle around the axis. So right here at the center of the representative rectangle, I have the x coordinate. We'll call it x sub I, and we'll call this representative rectangle the ith rectangle. Remember, we're breaking the region up into n rectangles. Here's the ith rectangle. Well, how would you find the volume of the ith disk that you get by revolving the ith rectangle around the x-axis? Well, it's just a disk or a cylinder, so it's going to be pi times the radius squared. But what's the radius going to be? The radius is going to be the y coordinate right here, and the y coordinate will be what you get when you plug x sub I, the x coordinate here, into the function. So that will be the radius of that disk. So we'll call this radius as a function of x sub I. So plug x sub I into your function f of x to get the radius of that disk. So pi r squared gives you then the area of that circle. And then you need to multiply by the height of the cylinder. But the height of the cylinder, the distance across that cylinder, is just going to be delta x. Delta x will be the cylinder height. So you multiply by delta x sub I. And the idea is when we break it into n rectangles like this, we're going to break them into n rectangles of equal width. So delta x will be the same for all n rectangles. So this gives you the volume of one cylinder, or one disk or cylinder that you get when you revolve this ith rectangle around the x-axis. So if you want to estimate the area under the curve, you have to add up all of the disk that you create. So you take the sum from I equal 1 to n. You broke it into n rectangles. Each rectangle, when you rotate it around the x-axis, will have volume pi r squared, the area of the circle, times the height, delta x sub I, pi r squared h, the volume of a cylinder. And then what we want to recognize is that pi is a constant, so constants can be factored out of summations. So if we factor the pi out of the summation, we'll just get the sum from I equal 1 to n. We'll get pi times the sum of r squared delta x sub I. And then to go from an approximation to the exact volume, what we need to do is, instead of we want to take the limit as n goes to infinity. We want to put infinity rectangles underneath this curve. And if we let n go to infinity, what we want to notice is that delta x will go to 0. As you fill the region underneath the curve with infinitely many, infinitely thin rectangles, these delta x's will approach 0 as we let n go to infinity. So we want to take the limit as n goes to infinity, as the number of rectangles goes to infinity. And we want to recognize that as n goes to infinity, delta x goes to 0. So when we do this, we actually get the exact volume of the volume of revolution. We get the exact volume instead of the approximate. And then we use calculus notation instead. So when we let delta x go to 0, our convention has been to take the summation notation and instead represent it with the integral symbol. So still an s for sum, just like this is an s for sum. And we integrate over the closed interval of interest. The pi is out in front of the summation. So again, this s here, the integration symbol, is just taking the place of the sigma notation here, indicating that we've let delta x sub I go to 0. So it's going to be pi r squared, and r usually is just going to be the function, right? R of x is typically going to be the function. We want to just recognize that function is giving us a radius. So pi r squared, there's the area of a circle times the height, delta x of I. But when delta x goes to 0, we represent it with a dx instead of delta x. So pi r squared h, where h is just dx. And there's the exact volume of revolution. So the only thing you have to then consider is, what if instead of revolving around the x-axis, you revolve around the y-axis instead? What changes in the calculation? And the answer is not too much changes. The radius now of your cylinder, so here's the cylinder over here, the radius of the cylinder is going to be x instead of y. So we'll need to know x as a function of y, or we'll need to know the radius as a function of y. And the slices these are delta y's, so they're going to become dx's. You're going to be integrating with respect to the y-axis if you revolve around the y-axis. So if we revolve around the y-axis over some closed interval from c to d, if this is the ith rectangle, the calculation would run the same as it just did. The volume of the cylinder you get when you revolve the ith rectangle around the y-axis is going to be pi times the radius squared. But now, instead of being a function of x, this radius is going to be a function of y sub I, the ith y coordinate. And instead of delta x, it's going to be times delta y sub I. So pi r squared, area of a circle, times height, area of a cylinder. This is one of the n cylinders if we cut this region up into n rectangles of equal width. So delta y is the same for each rectangle. And then we want to add them all up. So there's from 1 to n rectangles. The pi is a constant. It still factors out front just like it did on the previous slide. So I equal 1 to n. And then we want to take the limit as the number of rectangles goes to infinity, which means delta y will go to 0. And when delta y goes to 0, we call it dy instead of delta y. So we take the limit on this as n goes to infinity, which lets delta y go to 0, which means it's really the integral, pi times the integral, pi times the summation. But in the limit, we do pi times the integral from c to d. We want the radius as a function of y. Because the radius is an x value, we need to describe x in terms of y because we are integrating with respect to y. So here's a summary of the two different formulas depending on whether you're doing a horizontal or vertical axis revolution. Again, we don't have to revolve around the x or y axes. We are allowed, if we're working in the xy plane, to choose to revolve around other axes, and we'll deal with those types of examples when we get to them.